We're very happy to welcome this afternoon Dan Lee. She's a graduate from MIT, and so we're so lucky to have Dan with us under the MIT Africa partnership. And so it's a great pleasure to have her spending 4 months with us, working on very interesting projects. However, this is not the topic of her talk today. Today, she'll be talking of things that she's been doing back there in the US, and she'll be talking about solar cars. And she was very much involved in the construction of one such car at MIT with a group of some 25 to 30 people there, and also about ballroom dancing. So I'm not sure she'll be exhibiting a dance, but she'll be talking of ballroom dancing, and seems that there's some kind of connection. She'll take us to all this. So without any further ado, I pass on to Dan. Thanks, Dan, for your promptness to give a talk. She's here since the 17th of January. So it's not been a long time. But you know, it's important for her to also talk to you people, and she's so passionate about what she does, and I hope she can convey to you that, you know, that hard-won passion. So the floor is yours.
Thank you. Okay, hello, I'm Diane. So I'm going to start, hopefully. Okay. A little bit of background just to recap. I recently graduated from MIT with a degree in mechanical engineering and material science. And some of the things that I've been involved in there, one is solar car, another is ballroom dance. And as Sanjay mentioned, I'm here as a part of the MISTI Africa program. So MISTI is MIT's International Science and Technology Initiative, and they do exchanges around the world. Yeah, so my interests are generally in energy, climate, and sustainability topics. And some of the things that I've worked on before is I was an intern for Tesla's battery engineering team, and also worked for Heirloom Carbon, which is a startup that works on direct air capture. So what they do is they remove carbon dioxide from the atmosphere to reduce greenhouse gases. Okay, and what I'm here to do in the 4 months that I'm here is I'm working at Medina Agriculture right now. And there's a collaboration with a company called MycoHab. And what we do is we start with agricultural waste, and we can use that to grow mushrooms. So the mushrooms are used for food, but then the waste material inside the bag can then be used again to make new products. So the sorts of things that we're looking into are like styrofoam replacements or also structural materials. But today I am here to talk about solar cars and ballroom dancing. So just to give you a sense of the types of guiding questions I want you to be thinking about. For solar cars, I want to cover a little bit on what the potential of solar cars are, and also what's the limitations. And then I also want to dive a little bit into how they're built, so the critical aspects of the design and construction of solar cars. On the ballroom dancing side, this is a little more obscure as a topic maybe, but I want to talk about the process of experimental design, so how we can leverage technology to answer open-ended questions, how to make sense of the data and get answers to those questions. And communications had a little bit of a hard time because they're completely unrelated projects. But what's tying everything together is MIT's motto, which is Manus, which means mind and hands. So the idea is that education at MIT is driven by learning by doing. So the types of things that I want to focus on are process and execution. So how to start from an idea and then bring it to a final end product. And also to cover why practice is essential to all things STEM. Okay, so we're starting with solar car. And for anyone who has never seen a solar car, this is approximately what they look like. Why do we do this? Why are we students building a solar car? Well, it's all for a race. So there's actually a couple of these around the world. There's one in Australia, and there's also one, I think, in South Africa. But this one is called the American Solar Challenge. And the goal is to design and build a road legal vehicle that drives through 4 US states and 1,500 kilometers entirely on solar power. So we drive for about a week just across the country on public roadways. To give a sense in Mauritian terms of how long 1,500 kilometers is, that's around 4.5 times driving around the coast of Mauritius. Yeah. Okay, so the team. The team is an entirely student-run group. So there's about 40 of us, and we're mostly undergraduates. So the types of people who are working on the team are mechanical engineers, electrical engineers, computer scientists, and then also some material scientists or people studying aeroastro. So all of these kind of different disciplines come together to make a solar car. One of the super cool things about my team is that the MIT team is actually majority female, which is super rare in most engineering things. So when we go to competition, it's kind of funny because we'll go into the girls' bathroom and it's mostly just MIT students because very few other teams have female engineers. And the car. So when we talk about like car design, and especially solar car design, the first thing that you should always start with is an energy budget. How much energy do I have to run this vehicle? And our solar car runs about on 1 kilowatt of power, which to give a sense of how much 1 kilowatt is, that's about a toaster oven. So we are driving a car that is powered with the same amount of power that you use to make toast. Yes. Yeah, and that means that we need to really heighten our design to meet this power budget. So the two things that are most important is one, it needs to be super lightweight, and the other is it needs to be super aerodynamic, because that's where most of the energy goes. So does anyone have any guesses as to how much the car weighs? You can also think about it in terms of like compared to a normal car. What is it?
A few hundred kilos.
A few hundred kilos, yeah. So our car, without the driver, is around 180 kilos. And that's like 3 people can lift this thing. And to give a sense of like how much a normal car weighs, I believe it's around 1,000 kilos. So,
But tons, 3,500 kilos.
yeah, the smaller cars weigh yeah, around 1,000. Yeah. So we're like an order of magnitude under a normal car weight. Yeah, so that's the lightweight aspect of it. And the other part is it needs to be super aerodynamic. So it's actually very small, very low to the ground. And we have what's called an asymmetric catamaran design. So what that means is it's similar to like a catamaran boat, where you have like 2 different wheel wells, and that is shielding the wheels, and there's nothing in the center. So that lets more air flow through by decreasing the cross-sectional area. Yeah. So some more specs to give a sense of how this operates. It can go about 300 kilometers on a full battery charge. And we also run at 65 kilometers per hour net neutral. So that means that under full sun, without any battery energy, you can just keep driving for 65 kilometers per hour. Yeah, our top speed is somewhere around 110 kilometers per hour. Yeah, which is great because that's kind of what you need for the public highways. We do hold up traffic sometimes, but we try not to. Yeah, so our team is divided into 3 different subsystems. There's mechanical, electrical, and aerodynamics. And you can kind of see, I've shown some of the photos here. So aerodynamics is responsible for making the outer shell of the car. Electrical is responsible for the battery and the solar array. So we get energy from the sun and that charges our battery so that even when you have clouds passing or it's raining, you can still drive. And mechanical is everything that makes the car a car. Yes, just for fun side, this is Ryan Reynolds. Yay! So our solar car was actually in the movie Free Guy because they were filming in Boston and they were looking for experimental vehicles to be a part of the movie. So we actually got a really sketchy email that was like, be in movie, make $. And someone responded. So we ended up being in like the last part of the movie when they switch into the new world. Our car drives across the screen. Oh, thank you. When I was in solar car, my first year I was in aerodynamics and composites, and my second year I was the mechanical team lead. So I'm going to go a little more into the mechanical subsystem to give a sense of how we go through this design process. Yeah, so these are overviews of the mechanical subsystem. When we start a design process, we always want to start with design requirements. So thinking about a road legal vehicle, we think about what does a car need to do? So again, if the audience cares to answer, this one's a lot easier. What does a car need to do? It needs to move, okay. Forwards and backwards, yes. What else? Okay, so moving, but also I would recommend safety, yes, that's very important. In addition to moving, I recommend stopping. I think that's also pretty good. Anyone else? Any other thoughts? Yes, turning, very important.
So you're talking of a cab.
Huh?
A car acting as a cab.
A car, any car. Okay, yeah, so we can kind of translate these into subsystems. So moving, acceleration, stopping, brakes, turning, steering, right? Wheels are also pretty useful for rolling, suspension for when you're driving in the fields and there's a pothole. And also driver safety, very important. You can see in parentheses, comfort is a little bit lower on our list, but it's still present. Yes. Yeah, so going on from design requirements, then you can think about what does an assembly need to do? And in smaller resolution, what does a part need to do? And when you answer all these questions, it looks something like this. So ours is a 2-year design build cycle. So we spend 1 year on design and 1 year on building. Starting from design requirements, then you go into some of the calculations of, how much force does this need to withstand? Like, is this material strong enough? Can it withstand the temperature ranges? Those are the sorts of things that we consider when we design. And all of that happens on paper before it goes onto the computer. So what is shown here is computer-aided design. And those are renderings of the parts and subsystems that then go on to make on the whole car. Yeah, we also do what's called FEA, which is finite element analysis. And that allows us on the computer to simulate if you add this much force, what happens to your part. And then we build it. So we spend a year building our car, and about 80% of our vehicle is constructed by us as students. Yeah, so we have a machine shop in our garage, and we have machines like mills and lathes that are used for metal cutting. Also water jet, these are probably unfamiliar to non-engineers. But yes, they're basically a bunch of large machines that we can use to cut metal. And you end up with something like this. So you take that design that you have on the computer, and then you figure out how the machine and what tools it can use to cut out that shape from a block of metal. So that's what's called subtractive manufacturing. If you've ever heard of additive manufacturing, that refers to things like 3D printing. We very rarely use 3D printing because it's typically not as structural. But we do actually 3D print our steering wheel out of like a carbon fiber composite. The other thing that we do is that we need to assemble all of our parts together. So this top picture here is assembling our composite chassis. So composite material is a material that's combined out of different classes. So for example, you have polymers and metals, and our chassis is a combination of carbon fiber and aluminum. And that's all for the goal of being super lightweight. Yeah, so we assembled those in-house. This is a suspension assembly, and over there is our accelerator pedal. And the final step that you absolutely cannot get away without doing is testing. So testing happens on a lot of different scales, right? So you can do prototype testing, and that's kind of what you see in the top corner. Is before we built our actual chassis, which is extremely expensive, we cut a smaller version and we try to assemble that and make sure that everything fits reasonably, and the assembly process makes sense. You also do things on a material scale. So our chassis, like I mentioned, is a composite material. So it doesn't have as well-defined properties as, for example, steel. So what we do is, this is called instrument testing. So there's a machine where you can apply a certain amount of force and you can see at what point it breaks and how much it bends and that sort of thing. Yeah. So those are smaller scale. On the larger scale, we also do systems testing. So when you show up at the race, before they let you onto the public highways, you need to prove that your car works and is not a danger to your driver or other cars. So some of the types of dynamics testing that we do is we do figure-8 testing. So how fast can you go in a figure-8? Also, we do slalom. So there's a series of cones on the ground and our driver has to go through in 11 seconds. Yeah, so we pass systems level testing. Design-wise, we also do validation testing. So the aero shell is, for example, something that once you build, you can't unbuild. It's too expensive. But what we do is we need to validate how does this design compare to how we expected it to perform. So we actually also do wind tunnel testing, sponsored by Ford. We use their wind tunnel and you can see the aerodynamics of our vehicle. Yeah. And finally, before all of this goes on the road, the team has to go through operations testing. So that's an example of us driving in the streets in Cambridge. Yes. And just to wrap up this section on solar car, what my team captain always says is the car is only as good as the team that races it. So you can have the best designed car, but if you're not well trained as a team, if you're not able to coordinate, like navigation directions or strategy of how fast we're driving at what point in time, then your car is not going to win the race. Yeah, so that's one of the things that we pay a lot of attention to is building a really strong team, because that's what makes our car the best. Some of the unique challenges that I want to highlight of having a university team is that you have very limited incoming experience, right? So we are not asking people to apply to join the team and we're not interviewing people. We just take anyone who's interested. And then being on the team is the learning experience where you learn how to do these things like design analysis and machining and putting it all together. There's also, because everyone's only there for 4 years, there's a super high turnover rate. So one of the challenges is making sure that we document our knowledge and transfer it from one class year to the next. And finally, variable commitment, because all of this is on top of being full-time students. So imagine having your entire class load and then also building a car on the side. So it's hard to ask people, no one's getting paid for this. It's hard to ask people to be there and to make the deadlines. So that's something that, again, like we as a team need to manage. Yeah, but the reasons that I love it anyways is, first of all, because you get to see a full product life cycle. And this is something that's really rare in internships because you just don't have the time to start with the design and end up with something in your hands. But for us, we really start from zero and then end up with a car. Learning by doing. A lot of my engineering is based on the learning that I did in solar car. So having intuition of whether or not something will work comes from this practice and this experience of having built something. And of course, it's one of those once in a lifetime things that truly, why else would I drive across 4 US states? And I will pause here for questions about solar car. Who drove the car? That's a really good question. So our driver criteria is 1, you need to have a license. Yeah. And 2, you need to fit in the car. And 3, you have to have like a certain lack of fear. Yes, so we have 4 drivers who have fit this criteria during the race and they kind of alternate. I think 5-4 is about the height limit before your head starts hitting the top. Yeah. Yes.
Like with the drivers. Now, what's the maximum weight limit for the driver?
Yeah. So I talk a lot about being lightweight, right? So you would imagine that we just take the smallest people, we shove them in. But actually no, because in order to be fair to the competition, what happens is everyone needs to be ballasted up to a certain weight. So if you're under 70 kg, then you need to carry lead shot bags that go in the car that put you up to that weight, and that makes it even competition.
So if I understand properly, this is for racing.
Yes,
So obviously you need a car with only one driver.
yes.
But what if you would like to extrapolate that to for carrying passengers and so on?
Yeah.
So I mean, does everything change?
Yes,
It is.
absolutely, everything changes. Yeah, so I guess the thing is that this race has two parts. There's one class that's single occupant, that's called the Challenger class, and the other is multi-occupant vehicles. Yeah, so there's actually a subgroup of this race that specializes in 2 or 4 car vehicles. 2 or 4 person vehicles. And they need to compete separately because like their design criteria are entirely different. Yeah, so I want to leverage that to talk a little bit about the practicality of this. Any guesses as to how much it costs to build a solar car?
$200,000.
You're actually exactly on the money. I'm so shocked. I did not teach that answer ahead of time, but yes, it is $200,000. And that is not including labor. We work for free, then it's just like materials and construction that costs $200,000.
You should be given a chocolate bar.
Yeah. I don't have a prize, but
I was asking if you guys won a race before.
yes, we won the past 2 races.
Okay. And you were captain.
No, I was, actually thankfully, no. I was mechanical lead for one of them.
That's the lead.
I just to continue a little bit on the practicality part of it, the people who are doing multi-occupant vehicles are doing partial solar and then partial wall charging. So it's hard to like run a car with multiple people on just solar, or it's impractical. So yeah.
I've heard the question.
Yes.
For the races, they use the fuel, traditional method of the. What's the difference between what is consumed in terms of fuel and energy to this car compared to this one?
Yeah. So I can talk about it in terms of power. This uses about 1/6 the power of an average car on the road. Yeah.
What happens to the car?
Yeah, so we have a solar car graveyard as well, which is a parking lot where our old solar cars go to die. But one of our previous ones we donated to another university team so that they can like get started on like testing and design and that sort of thing by working off of our previous car. Another one we're hoping will go into MIT's museum.
You not reuse the parts.
You can reuse some parts. Some things like the motor, we will take off and reuse because that's something that we purchased and it's very expensive. The rims and the tires as well are really hard to source because they're specialized for solar car racing. So the things that are very difficult to like purchase again, we will reuse, but actually a lot of it we build again from scratch. One, because the design changes. But also so that our new team has that experience. How many what? How many solar cars from our team or in the race? Our team started in the 1980s. So I think probably less than 10 solar cars. Yeah, from our team. But in the race, there's a lot of other universities that also participate. By a lot, I also mean like 10-ish. Yeah. So yes, there's not that many of them.
So Dan,
Yes.
when you started building the car,
Yeah.
you must have gone to other people who've already done that.
Yeah.
Right?
Yeah.
So how do you compare yours with what has been done previously?
Yeah, that's a great question. So the first people that we go to is the retiring team members. So they're our repository of knowledge. But comparing to other teams, a lot of older solar car designs did not put the driver on one side, they put the driver in the middle. And that is a lot better for mechanical design because you have a balanced vehicle and your brakes are the same on both sides. For us, since we put the driver on one side, then we no longer have a symmetric braking system, and each individual brake pad needs to be tuned to the weight distribution of the car. Yeah, so that's one change. So it's more difficult mechanically, but the reason that we do that is because it's better aerodynamically. So if you imagine having someone in the center of the car, what I described as a catamaran shape now has an extra bump in the middle for a person to sit. And that increases the cross-sectional area, which greatly increases the amount of drag that the car experiences. Yeah, so that's one example.
And so after doing this, did you think of having a patent, for example? Because you've been doing things original.
Our team is mostly just focused on the race. We don't, so the thing is, because it's entirely student run, we don't necessarily have the resources to go through the process of like patent application and this sort of thing. I think there are also already some companies out there that are working on solar car design. Personally, I don't think it's
$200,000, yeah.
Huh?
It cost you $200,000.
Yes, that's true.
It's a huge amount of money.
It is a very large amount of money. Yes, we fundraise by going to sponsor companies. So, for example, Ford and some companies donate our like carbon fiber materials. Yeah, that's also part of like the student team experience. It's like you go through everything from like team management to fundraising and that sort of thing. Any other questions?
What are the maintenance like on tires, like after the race? How often do you use the cars in the race? Like, how many races do you use?
So the car that I was showing in the pictures, we raced for 2 races. Yeah.
The tires, like say you have something like, I don't know how the tires are, let's say you have a puncture or something.
Yeah.
Since you said something about the shell.
Yeah.
Where you kind of open it up.
Yeah, so the way, yes, maintenance is actually like, it's super important to design for maintenance. So let me see if I can show you a picture of like where we take things off. So this is the shell and it looks like one piece,
Yeah.
but actually there's a seam down here. So the entire top comes off. The top comes off, which is one important for like getting to things inside, but also at the beginning and the end of the day, we have a charging period. Because the sunlight is at a slanted angle and that's not enough for us to run. So we stop the car and then we tilt up the array and we charge by facing it towards the sun. Yeah, so that's one of the seams. And the other is around each of the wheel wells. We can also take those off. So it's just like a thin carbon fiber shell and you take it off and that gives you access to it. Yeah, so for example, during one of our races, our tire popped. So we had to do like a pit stop on the side of the road and shake it out. Yeah. Yeah. Any other solar car questions? Okay, great. I think
So
we are.
maybe if we are to extrapolate these separations, we can think of using scrap material that are not being used, and we can at least give another lifetime for this material, because we've got old cars and we can use them eventually for whatever purpose we have, at least the body of the car.
Yes, yeah, I think to some extent you can, but it would be difficult to do a fully solar powered. You would want to do like a partially solar powered and partially battery powered.
Yeah, because of the weight, yeah.
Yeah, because of the weight.
Okay.
Yeah. Yeah, so solar panels are actually only around 25% efficient. Yeah, so that's like 75% of the sun's energy is just not going to powering the car. Okay, so we will start a little bit on ballroom dancing. We don't have too many people in the audience, but in the spirit of learning by doing, I am looking for audience volunteers. In particular, ballroom dancing is partner dancing. So I'm looking for pairs of people.
They actually dance.
Groups of 2. Anyone? Any willing members?
So we will prefer those students to find.
But we could also take UEH staff.
There you go. The experience stuff, no, that's.
It'll be super easy. So I'm going to take you 2 because. Thank you very much. Can we also get some UEH staff to join us? a group of two.
Yeah, energy coming up.
We have to, we're in person, so we need to take advantage of this, you know?
Yeah.
We could also pick Andre. You can come. You can, yeah, you can pick with Didi. It'll be super easy. I will tell you exactly what to do.
Yeah, no, I mean, it's just for her to get the.
Side takes to view.
Oh, thank you. A round of applause for our volunteers. Okay, so to explain ballroom dancing is partner dancing, but it's not choreographed. So we're going to start with something that's choreographed, just to give a sense of how it works. And then we'll talk a little bit about the challenges of ballroom. So I need each of these groups to pick a follower and a leader. Okay, and leaders, I want to stand on this side and followers on this side. Okay, face your partner, so. Okay, wait, who's?
Yes.
Okay, so we have our leaders and our followers. Yes, is this what we've decided?
Yeah.
Okay, so I want the leaders to make a frame like this. Okay, and I want the followers to join their partner like this. So you want to put your arms on the inside, yes, and then your hands should go against my elbows. Okay, great. So in something that's choreographed, for example, right, I would tell you when to walk, which foot to walk with, and how far. Okay. So I will stand on this side just so the leaders can see me. I'm going to count 5, 6, 7, 8, and then you're going to step with your right foot. 1, left foot 2, and then right foot 3, left foot 4. Okay. Okay, so it will be
Move with forwards.
yeah, it will be 5, 6, 7, 8, and then 1, 2, 3, 4. Okay, and then I will do it from the follower's perspective, right? 5, 6, 7, 8, and then 1, 2, 3, 4. Okay, are we good? Okay, 5, 6, 7, 8. 1, 2, 3, 4. Okay, one more time. Okay. 5, 6, 7, 8. 1, 2, 3, 4. Wow, amazing. Okay, next one here. Okay. Now it's going to get a little harder. Because I'm not going to tell you when to step, where to step, how many steps. So the leaders are going to decide for themselves. And you're just going to walk either forwards or backwards, which leg you decide. And you can try with your followers. Okay.
Can I request a golf swing? Very fast.
Lectures are so much fun.
Go on, me on.
Okay, as you please. Okay, so to ask our partnership, what is difficult here? What do you find challenging?
No communication at all.
No communication at all. Okay.
She's stepping on my foot.
Okay, so this very well demonstrated is the difficulty of ballroom dancing. It's like, for me, I've done a lot of different types of dances before, and this is really frustrating to learn because for like half a year, you're just learning to walk again. And it's because it's a partner dance. So you as an individual aren't deciding what's happening. It's a communication that happens between the leader and the follower, but it's a communication without words. So the next thing that I'm going to teach a little bit of is how to talk to your partner, but without words. So for our leaders, so the first thing, right, that is difficult is like, which leg do you start with, right? So when you're in a practice hold with your partner, right, what you can do is you can practice shifting weight. So you could try this with your partner. You could shift weight, and that'll tell you which foot to start with. Okay, so you can shift weight, right? Yeah, so when you shift weight, the leg that doesn't have your weight is the leg that takes the step, right? So as you prepare, then the next step is what you do. Does that make sense? Okay, so if your leaders shift weight to the right foot, then the left foot is the foot that takes the step. Does that make sense? Okay, so that's the first part. And the second part is you go forwards or backwards and when. So that's what I was taught as the cradle. So what you can do in your hold is if you're going forward, leaders can push inwards and that can guide the follower forwards. Versus if you want to go backwards, right? Then you can start to open up and leave space for someone to follow. Does that make sense? Okay. Okay, so can we try that? So try first shifting weight to figure out which foot to step, and then tell your partner whether to go forwards or backwards. Oh, okay.
How much you need? I'm not doing shit. I'm probably
Hard. Okay, and that is as much as I will teach for now. But thank you very much to our volunteers. Y'all are so great, thank you. Yeah, so that is why ballroom is difficult. And we're just walking forwards and backwards right now, but actually it gets more complicated. So here's just a sample of what happens in a tango. Yeah. So what is being demonstrated here is the tango reverse turn. So it's a 6-step figure, and that means you're taking 6 steps in 8 beats. And the leader will go, well, let's see if I know it from the leader's side. Actually, I'll start with the follower side. So follower goes back 2, 3, forward 2, 3. And then from the leader side, there'll be the natural opposite. So forward 2, back, and then back, switch to forward. Yes. Yeah, so that's what they're doing here. And me, after retiring from solar car and starting up ballroom dancing, decided that this was actually very confusing. So the question that I have is, how do dancers use touch to communicate when and where to step? And I was taking a class called Measurement and Instrumentation as a part of mechanical engineering. So what we did, oh, you cannot see gray on this projector. That is really tragic. I wonder if you can see it from here, maybe. Yeah, it makes more sense now, doesn't it? Yeah, so this is the experimental design that I started with, is to have an experienced partnership. So that was my instructor and his partner. And I taped force sensing resistors to their hands. Which the way that works is it's what's called a piezoelectric material. So it responds to pressure and it creates an electrical signal. Yeah, so that was taped to their hands and also another one to the elbow. And data was being collected in a machine on their backpack. And then what I had set up is I had 3 different colors to mark a short distance, a middle distance, and a long distance. So knowing that the dance step that they were doing was the tango reverse turn, I asked them to dance to different distances, but I would only show the leaders. I would only tell the leader which distance to go, and the follower would have to figure it out based on the leader's signal. Okay, let's see the next one. Okay. Yeah, so you run this experiment about 24 times, and this is what you get out, which is actually a lot of nonsense. If this is raw data, it's actually super useless for a couple of reasons. One is that I want to measure force, right? But if you can see on these sides, which you probably can't because it's really small, but this says potential, and it's voltage. And that is because the signal that's being measured is being measured as an electric signal. So I'm not getting force measure, I'm getting a voltage measure. The other thing is that I'm playing this and they're not necessarily starting at the same time. So none of the data is synced time-wise, right? So you can see the signals that don't overlap and their times are shifted. So in order to make raw data useful, I need to do two things. One is to scale it to be a measure of force instead of potential. And another is to cut and trim and sync everything together. So I do that and I get this, which is better, but also useless. Yes, so on one hand, this is the measurement from the hand. And on the other side, this is the measurement from the elbow. So what I've done is I've changed them into force scales and I've synced them on time. So you can see now the beats of the step, right? So you can see time-wise, right, at 0. Here, this is a baseline before that, right? And then 1, 2, 3, 4, 5, 6, 7, 8 is the beat of the step. So how to make sense of this? The first thing to do is to take an individual data run and see what you can tell. What is the story that's happening in this data? So this is a single run, and it's happening in the longest distance. So you have one signal from the hand and another signal from the elbow, and you can see them as distinct. One thing that's immediately interesting to note is they kind of alternate which one goes up and which one goes down. And then another thing is that there's this very interesting dip over here. So I will point that out for now, and we'll see what happens as we analyze a little more. So for the hand, we can start to find patterns. So what I've done here is this is an average of each of the signals for each of the distances. So the 3 distances, short, middle, and long, each one has 8 trial runs, and that data is average. So its projector isn't showing it very clearly, but it's also showing a 90% confidence interval of, like what is the average of each run above and below this line. Something that you can tell immediately is that they have very similar signals. So you can kind of repeat the signal from one distance to the next, but they have different baselines. So what we can do is we can plot the force for the maximum force and the baseline force. And for the maximum force, it has a slope of 0.9 plus or minus 1.5. So what that means is that the uncertainty makes the slope such that it could be 0. There's not necessarily a distinguishable difference in the maximum force. However, for the baseline force, we have minus 1.9 plus or minus 1.4. So because this uncertainty is less than the value, that means that there is a significant relationship between the baseline force and the distance that's being traveled. Yeah, so one conclusion that we can make of like how signaling is happening is that for the longer distances, the original baseline force is lower than for the shorter distances. And the next part is the elbow. So what's happening here is that you again have the 3 different averages, but these ones actually signals look really different from each other. So unlike the hand that had a similar signal between distances, this one shows a very different signature from one distance to the next. So I was looking at this and trying to make sense of this. But this is where I pointed out earlier that you have a dip in the long distance, but you have a hill in the short distance. And actually what's happening here is I mentioned that the way the leader moves is you go forward and then you turn around, right? And then you keep going. So in the turning around, that's what's happening around here. It's this turning part, right? So I'm going forward and I'm turning. So when I'm going a longer distance as a leader, right, the way that I can signal to my partner that we're moving far is that I take a larger step and I release the pressure here. So when I release that pressure, that's this dip. And that's the invitation, right? It's not that I'm like pulling someone forward. I'm releasing the pressure to invite the follower to take a larger step forward. Does that make sense? Yeah. And like the difference, right, in the short one, right, is you don't see that dip, right? What's happening instead is the leader is stepping here and they're saying, okay, we're not moving that far. So they're keeping pressure here to say, take small steps as we keep going. Does that make sense? Yeah. Yeah, so I thought that was really cool. As a novice to ballroom dancing, I just wanted to know, like, how are they talking to each other? And this is how. And another thing that I want to point out is the cradle that I mentioned before in our teaching. So part of the question is when do you start, right? Like, how do you know when in the music that you should start walking? And that's what you're seeing here, that even before beat 0, right, you're getting a signal that, hey, we're about to step. Yeah, so data patterns, yes. And this kind of, whenever you're doing a research project, right, you kind of always end up with more questions than you started with. So some things that came to mind for me were, what does the force signal look like for a different partnership, right? So this was a group of 2 experienced people. What does it look like with 2 novice people? Let me just check time. Another is for a different dance step, right? Can I look at a signal and say, hey, this one's a tango reverse turn and that's like a waltz natural turn. How does the force signal compare between experienced and novice ones? To what extent does the follower rely on audio-visual cues in addition to touch? So in this experiment, I did not blindfold my follower and I did not make them wear earplugs. So that means they could still see like which way they were going and they could still hear the music, right? So I'm curious, like if, for example, only the leader, right, was listening to the music and then the follower wasn't looking at anything, right? If they were blindfolded, for example, would you still have this amount of accuracy in achieving the distances and stepping on? Yeah. And then this all so far has just been purely out of interest. Nothing really applied here, but you can start thinking forward into the engineering side of how might this knowledge of haptic communication, which means communication by touch, be applied to improve the design of assistive technology. So thinking about, for example, you know, if we need robots partnering with humans, right? How does touch signaling maybe work between a robot and a human partnership instead of a human one? And that is all I have for today. So, any questions? So we can do questions related to dancing part, to solar car, to MIT, to literally anything. So go for it. Or mushrooms. How can we talk about mushrooms?
Have you seen blind people doing such dance?
I have not. I have not. So I've only, this was my retirement activity after solar car. So I really only did it for 1 year. Yeah, so I haven't been in the space enough to see, but I have seen experienced partnerships. The follower can close their eyes and still dance.
Yes.
Yeah.
Is that full answer?
Yeah.
I would guess that it's just by there's no visual difference. I would guess that there's no visual.
Yes.
They don't use anything visual. It's
Yeah.
just by, you know, as you say, it's just by low pressure that they exert.
Yeah, yeah. So
Signal.
for me, in my experience from dancing, I do use visual cues to help. So for example, one thing is like you're competing on a competition floor with a lot of other couples. So no one's choreographed. So you need to navigate the space at the same time as everyone else. And like out of the corner of my eye, I will be looking for, are we about to crash into something? So beyond the cues that I'm getting from my partner, I'm also like supporting that with visual information of like obstacles and barriers. Yeah.
It's just me saying that you're really cool.
I appreciate that. Is there anything from online? Do we have online? Yes.
Hi, since you so would you say that your friend just mentioned just now about being very cool? Is that something that you believe the culture MIT has brought out in you?
Yes. Thank you for this question. I honestly, the people at MIT are cooler than I am. Like there are so many super cool people. Yeah, it does rub off a little bit. Yeah. So I think like one of the super amazing things that I wasn't expecting about MIT, but I found when I got there, is that there's most people live on campus. So individual dorms have like different cultures and a lot of different student activities. So for me, like the extracurriculars that I'm showing here are just like a pin in like the whole scape of like what's available, right? So there are people who do theater, a lot of a cappella groups. Besides solar car, there's a race car team, a rocket team, marine robotics. So there's like truly like all sorts of things going on around campus, and yeah, it's a very cool place to be.
My next question is, have you visited the particle accelerator at MIT?
So the particle accelerator. Yeah, I haven't visited it.
I heard about that.
Yeah, particles scare me a little bit. So
Thank you.
How did you come up with the idea of ballroom dance, which I feel like you love very much, especially the way you thank you, combining it with what you learned in MIT engineering? How did that idea come?
Yeah. So basically, there's a class where part of our required classes are communication for the pencil. So one of them is a product design class, and another is measurement and instrumentation. So as a part of measurement and instrumentation, everyone gets an individual project that you design yourself based on any topic that you're interested in. So actually, I have a friend from Solar Car who, when she took the class, she wanted to measure how squishy stuffed animals were. So she got like 3 different plushies and she just squished them in a machine for a certain number of repetitions, and then she would turn them over and she would squish them into different axes. So this class gives you an opportunity to do anything you want. And for me, because I was learning ballroom dance at that time, it was something that I really wanted to try to measure, something that I couldn't see.
Do you have any plans of doing something with this, or is it just for personal research?
Yeah, for me, it was mostly just because I had this class and I needed a project for it. And also like the interest from learning to dance. Beyond that, I don't really plan on doing it.
Do you think your technique or your discovery based on ballroom dancing can be used in academies?
Used in what?
In academies like dance.
Oh yeah, honestly, I think it's useful. Like I feel like this sort of thing, if it were like explained to me in this way, like I learn things very visually. So to be able to see like that dip, right, is very instructive of like at this point in time, right, like release the pressure, right. So I think I wanted to look at it from a teaching perspective. So hopefully, but I don't know that anyone will pick up on this. Yeah.
Do you think it can be taught by someone?
How by sign
You know, like the Super Bowl as US, we're gonna have our own like sign language performance. So those who were deaf, be able to dance,
Yeah.
understand the movements,
Yeah.
the beat that she exuded out of sign language performances.
That's awesome. I did not know that. But yes, I definitely think that ballroom can be taught by sign language because it's one of those things where like you learn by the experience of doing it, right? So like you can't get a sense of like how it feels until you actually do it, right? And especially being a partner dance, right? That's something where one partner can teach the other partner.
I also don't think that it's necessary for anything to be applied. What I see from what you have been doing is trying to understand the science behind the dancing language.
Yeah. Yeah.
Right? So there is something that is being done, and you try to explain scientifically how it is being done.
Yes. Yeah.
Right, but probably people have been doing that for decades and for years.
Yeah.
Yeah, they've been doing such kind of things, but without necessarily looking at how the science works.
Yeah.
So you use instrumentation techniques and so on to explain how this is working.
Yeah.
So science is behind a lot of things.
Yes, yeah, so that's actually a great point that I should take a moment on. The two examples that I've given, the first one is more of an engineering example, and the second one is more a science example, in the sense that the second one isn't designed with application in mind. It's just purely out of curiosity and wanting to answer something. So.
I think we've reached the end.
Yes.
So I just would like to thank you, Dan, for giving a superb talk.
Oh, thank you.
I think that has motivated a lot of you into how we can use science through engineering to come up with real products, and how we can understand the world using science. So thanks a lot for that, and you've also shown to us how MIT works. I'm also given to understand that at MIT, if you are a science student or if you are an engineering student, you must do something else.
Yes.
That has nothing to do with your engineering or your science.
This is true.
And that is something great, because then you learn about the world and you learn about people, you learn about culture. So that's the good part of it. I think, I don't know if at Middlesex you also learn things outside of what you do, about your specialization or your bachelor or even your masters, doing other things. If you're doing, let's say, you're studying finance, I know you probably will not do anything scientific, but that could be interesting to also engage in some science.
Yes, it's very interdisciplinary. Yeah, for us, everyone is required to have a concentration in a humanities, arts, and social sciences area. So that means you take like 3 or 4 classes in a specific area that's outside of STEM. So for me, I did mine in urban studies. Took classes in international development, city design, things along these lines.
Okay. So thank you again. And we now look forward to the next talk in the month of March. And could be another graduate from MIT will be delivering the next talk. We'll see. She's not yet here, but we're still waiting. And if it's not March, it will be probably April or May. But we'll get one of your friends from MIT to give another talk. So thanks again.
Thank you.